Find all the rational zeros of the polynomial, then find the irrational zeros, if any. Whenever appropriate, use the rational zeros theorem, the upper and lower bound theorem, just Descartes' rule of signs, quadratic formula, or other factoring techniques. So pretty much everything we've learned, we're going to use all those tricks to factor this. So, first of all, let's do the rational root theorem, which says the factors of this divided by the factors of this. So it's going to be plus or minus 4, 2, or 1 divided by 2 or 1. So if I list them out, it'll be plus or minus 4 divided by 2, which is 2. 4 divided by 1, which is 4. 2 divided by 2, which is 1. And then 2 divided by 1, which is 2, which is already there. 1 divided by 2, which is 1/2. And 1 divided by 1, which is 1. So those are all my options that I can do. Now, if you notice, this never changes signs. So using Descartes' rule of signs, that means I'm going to have 0 positive zeros. Now, if I do p of negative x, I end up getting 2 times negative x to the 4th, plus 15 times negative x to the 3rd, plus 31 negative x to the squared, plus 20 negative x is plus 4. This gives me positive 2x to the 4th minus 15x cubed plus 31x squared minus 20x plus 4. And if you notice, the signs change every single time. So I could have 4, 2, or 0 negative zeros. But since I have 0 positive zeros, I can actually get rid of this right here. So using Descartes' rule of signs, that just got rid of half the options that I need to choose. So let's choose something that we have left over. I'm going to try negative 2 first. Using synthetic division, I end up getting 2, negative 4, 11, 22, negative 22. That's 9. Negative 18. That's 2. And then negative 4, 0. So that is a 0. Negative 2 is a 0. Now, I don't want you to think that this is a upper bound, mainly because in order for something to be an upper bound, first, if you have a lower bound and an upper bound, the upper bound needs to be bigger than 0. And this is not bigger than 0, so it cannot be an upper bound. Even though it looks like it could, mainly because these never change signs, but just remember, this is not positive, so it can't be an upper bound. So this factors out to be x plus 2, and then 2x cubed plus 11x plus 9, well, 11x squared plus 9x plus 2. So I'm going to move this up here. So now I can actually factor this instead of this anymore, which then means, using the rational root theorem, that the factors are going to be the factors of 2 over the factors of 2, which means that this no longer needs to be there, which gets rid of this option right here, so I don't have to check 4. So now let's check negative 1. So negative 1, and then we get 2, 11, 9, 2. So we get 2, negative 2, 9, negative 9, 0, 0, 2. There's a 2 there, which means it doesn't work. So now the last one we need to check is negative 1/2, which ends up being 2, 11, 9, 2. Bring the 2 down. Half of 2 multiplied by a negative is going to be negative 1, which gives me 10. Half of 10 is 5. That's a negative 5. That gives me a 4. Half of 4 is negative 2, 0. There it is. So this factors out to be x plus 2. Now x plus 1/2. 2x plus 10x, 2x squared plus 10x plus 4. Now remember, I can factor out a 2 out of this one, and then I can give it to this one. So factor out a 2 out, put the 2 back in here, and that gives me x plus 2, 2x plus 1, and x squared plus 5x plus 2. Now, I'm not going to check anything else because I just want to use the quadratic formula. So you get x equals negative b plus or minus the square root of b squared, 25, minus 4ac, which is 8, all over 2a, which is 2. So you end up with negative 5 plus or minus the square root of 17 divided by 2. So my zeros are negative 2, negative 1/2, negative 5 plus the square root of 17 over 2, and let me get some room over here. The last one is going to be negative 5 minus the square root of 17 over 2.